We start with an animated IG from Chapter 2, which is used to visualise, as a function of the stiffness of each spring, the total deflection of two springs in series, and the contribution of each spring to the total deflection. When the stiffness of the bottom spring remains fixed, the bottom spring does not compress further, as the stiffness of the top spring decreases. When the top spring remains fixed, the top spring moves as a rigid entity, as the stiffness of the bottom spring decreases. The displacement of each spring is independent of the displacement of the other spring. However, the total displacement of the spring combination is the sum of the displacements of the individual springs. The next IG is from Chapter 4 and is used to visualise the response of a single degree of freedom system to an initial velocity, initial displacement, and for different damping factors. Several important numerical values are displayed for the various responses, the extrema and the time at which they occur for the displacement, velocity, acceleration, and the length of time it takes for the system to decay within plus or minus 2% of its final value. Different scenarios can be examined: initial displacement only, initial velocity only, damping factor, note axis adjustment capability. The time-varying magnitudes always stay within the exponential envelope. As the damping factor approaches zero, the acceleration becomes 180 degrees out of phase with respect to the displacement. And the damping factor and the initial conditions influence the time that it takes for the displacement response to decrease within plus or minus 2% of its final value. The third interactive graphic is from Chapter 5 and is used to visualise the response of a single degree of freedom system to various periodic waveforms as a function of the damping factor, waveform period, waveform duration, and the location of the natural frequency of the system. Magnification by the resonance portion of the system's amplitude response function, H for omega. The amplification of the higher harmonic components causes the small magnitude oscillations about the waveform, and some semblance of the general shape of the waveform is preserved. The magnitude of these effects is different for different waveforms. When the lower harmonic components are amplified, the original waveform is greatly distorted and becomes virtually unrecognizable. Again, the magnitude of these effects is different for different waveforms, and the nominal waveform shape can be preserved by greatly increasing the damping factor. The fourth interactive graphic is from Chapter 7 and is used to display the natural frequency coefficients and animate the mode shapes associated with the first and second natural frequencies of a translating 2 degree of freedom system. The variations of natural frequency coefficient and associated mode shapes with respect of the natural frequency ratio and the mass ratio can be explored. The motions of the masses are in phase for the mode shape associated with the lowest natural frequency. On the other hand, the motions of the masses are out of phase for the mode shape associated with the second natural frequency . A decrease in the stiffness, K3, results in a decrease in each natural frequency. For the system with two masses and one spring, the lowest frequency is 0, and associated mode is a rigid body mode. And for the second mode, the masses are out of phase and their ratio is equal to negative mr. The last interactive graphic is from Chapter 8 and is used to display the frequency response functions H11, H12 and H22 of a translating 2 degree of freedom system as a function of the natural frequency ratio, the mass ratio, and the damping factors. In addition, the natural frequency coefficients are given for the selected parameters. Some things to note. The surface plot provides the entire family of frequency response functions for the parameters selected. And for an undamped system, the examination of H11 can be used to find a set of parameters at which the system can operate as a vibration absorber.